everybody. So today we are going to be talking about energy, work, and power. So let's get started. Another model of the world. So last cycle, or last academic cycle, I should say, momentum describes relationships between mass and velocity. So we said momentum was inertia in motion. It was this mass going in motion. So some situations seem to be more dangerous than others, though, like a brick sitting on your head or a brick being held above your head, or a drawn bow and arrow and an undrawn bow, a parked car and a car going 75 miles per hour. So, what's the difference between these situations? It has to do with energy. So, what is energy? And we want to think of energy as the ability to do something. Like the ability to cause damage. So, what situations are dangerous? There are more types of energy than just one. We have moving, we have stored, we have chemical, we have heat, we have electromagnetic, we have mechanical. So, there are a bunch of different types of energy, and we have to think of energy as the ability to do something or the ability to cause some type of damage, maybe. So let's get going here. We will mainly be concerned with mechanical energy. And mechanical energy comes in two basic forms, potential energy and kinetic energy. And we also refer to potential energy as stored energy and kinetic energy as energy in motion. Okay, so potential energy, that's stored energy, and kinetic energy, that energy in motion. All right, so the potential to do something and then actually doing that thing. So, potential energy. An object can store energy based on its position. This stored energy is known as potential energy, and we are given two examples here, the bowling ball held way above this person's face, and then a drawn bow and arrow. So, again, potential energy, we are looking at this stored amount of energy or this potential to do something. So, the stored energy, again, is known as potential energy. Potential energy when the bowling ball is on the ground or the bow is not drawn back. So neither is storing any energy, neither seems that dangerous. Right? We can see that that bowling ball is pretty close to that ground or that person's face, and the bow and arrow doesn't seem all that powerful, right? It doesn't seem like there's a lot of energy. It doesn't seem that dangerous. Potential energy again. So the change in the position and the danger has increased when we increase the height of which it's being placed. Right, so we can see that the distance from that person's face to the bowling ball is much greater. So we see that, we're a little bit more anxious. This has a little bit more energy to do some damage here. And that drawn back bow and arrow, again, this seems really dangerous to us. It has more potential to do things. So somehow changing the position of your object has made it more dangerous. And the main type of mechanical potential energy that we will be talking about in this chapter is gravitational potential energy. And we're going to talk about that in just a second. But we can see this little pendulum going back and forth, and we can recognize that at certain points on this timeline, we have more kinetic energy, we have more potential energy, we have a time where the kinetic and potential energy is the exact same. So we can just see there on that little graph that that little graph output shows us the different types of energy and also the energy total and how it's working with the pendulum as it's going back and forth. So gravitational potential energy is the energy stored by an object due to its vertical position or height, just like we saw previously with the bowling ball being held above that person's face or the arrow being drawn back on the bow. We increase the vertical position when we're talking about gravitational potential energy. We want to talk about in the y direction, that vertical position. So maybe the drawing back arrow wasn't the best example, but definitely that bowling ball above that person's face. So with that increased distance, we saw an increased gravitational potential energy. And where do you think this stored energy comes from? Well, it comes from gravity, this gravitational attraction to the Earth. So if you let it go, the force will act on the object and moving it, making it go faster and faster. And when things go faster and faster and faster, they actually accelerate downward more. So with that more, we have more gravitational potential energy. So that increased distance, we have more gravitational potential energy there. So gravitational potential energy depends on three values: the mass of the raised object, the height of the object of which it was raised, the gravitational acceleration constant, g. Everybody's favorite number, g. So can you guess what the equation looks like? Well, because of these three things and how gravitational potential energy all depends on these three things, then we can say that mass times g times height is your gravitational potential energy. And we usually say this as PE equals mgh when we're talking about that gravitational potential energy. And if we were to do this out, we'd see that the units are kilograms times meters per second squared times meters, which is kilogram meters per second squared over second squared, which we call joules. Okay, and joules we just label with a big J. So when we talk about energy, we're actually talking about joules here. Okay, so potential energy, again, it's a type of energy. It depends on your mass, your height, your gravitational acceleration constant, g. So we have mass times g times height, and that is your gravitational potential energy equation. Okay, so this is the equation that we're going to use for gravitational potential energy. So what happens to your gravitational potential energy as you walk up a flight of stairs? Well, because we're increasing that distance, we are going to see an increase in our gravitational potential energy. How does the gravitational potential energy of a bowling ball and a baseball compare to each other from the same height? Well, because the same height, we can see, that there is going to be a difference because there is a difference in mass. So the bowling ball's mass is greater, and as we know, gravitational potential energy depends on mass, g, and that distance. Well, we know that, again, if we were to do this math out, that the gravitational potential energy for the bowling ball is going to be greater because the mass is greater. So suppose you have a 1 kilogram book resting on a bookshelf that is 3 meters high. How much potential energy does it have? So we're just using our gravitational potential energy equation, which is mgh. Okay, so PE equals mass times your gravitational acceleration constant and your height. So we're given a mass of 1 kilogram. G to us is 10 meters per second squared, and the height of which it was being lifted, or the distance that it had to fall to the ground, was 3 meters. So if we did all of this math out, we would get 30 joules of potential energy. If it falls and lands on a table 1 meter high, how much did the potential energy change? So we want to take and solve for what is its potential energy when it's at that 1 meter height. Okay, so first we're taking the mass. Again, the mass isn't going to change. G is also a constant. And now we're at this new height of 1 meter. So we have 1 kilogram times 10 meters per second squared times 1 meter. And now we want to find delta potential energy, or the change in your potential energy. So we want to find the final minus the initial. So our final position was at that 1 meter mark. Our initial position was at that 3 meter mark. So we're going to take that 10 joules of potential energy, subtract it from that 30 joules of potential energy, and we get negative 20 joules. So how much did the potential energy change? Negative 20 joules. Okay, so we're going to see different examples of this, but this is just an example of how we are using this equation to solve for our potential energy. Now let's talk about kinetic energy, or that energy of motion. So kinetic energy is the energy of motion. If an object has motion in any direction, it has kinetic energy. So guess what the kinetic energy of an object depends on? You would guess your mass and velocity. Okay, so kinetic energy, again, it's the energy of motion. So the faster an object is going, the more kinetic energy it has. And also, the more mass an object has, the more kinetic energy it has. And the formula that describes the kinetic energy is 1/2 mv squared. And the units again are going to end up being kilogram meters squared over second squared, which again we know as joules. So kinetic energy, again, it's the energy in motion, and the equation for kinetic energy is 1/2 mv squared, where m is your mass in kilograms, v is your velocity in meters per second. So if we do this math out, again, we're going to get the units of kilogram meter squared over second squared, which we know as joules. So when we talk about energy, we're measuring it in joules. So again, Ke equals 1/2 mv squared. So kinetic energy is a scalar quantity. It does not have a direction, and it's completely described by its magnitude. The equation reveals that a mass increases and the kinetic energy increases proportionally. So if we increase this mass by double, then our kinetic energy is also going to be doubled. It also reveals that as the speed increases, the kinetic energy increases as the square of the speed. And again, we're saying speed because speed is a scalar quantity. Kinetic energy does not depend on direction. Okay, so we talk about speed in this case. So it also reveals that as speed increases, or as your v increases, the kinetic energy increases as the square of the speed increases. So again, kinetic energy is equal to 1/2 mv squared. M is your mass, v is your speed, and it's going to be squared. And remember that kinetic energy is a scalar quantity. It does not have direction. We only care about its magnitude. So if the speed of an object doubles, the kinetic energy increases fourfold. Okay, so if the speed of your object doubles, we're talking about speed, so that's v. If we plugged in a doubled speed there, we're going to see that the kinetic energy increases by 4 or fourfold. If speed triples the kinetic energy, it multiplies it by 9. And we can see this out later, but if you just want to plug in 1, 2, 3 into that v, then we're going to see that our kinetic energy is going to increase by that squared factor. Now let's talk about mechanical energy. So both potential energy and kinetic energy are forms of mechanical energy, and they often act together as objects of the same time. So let's try to see how they relate to each other. So at the top before the person drops, what is its potential energy and kinetic energy? So let's just say that there's a person about to fall off a cliff, like before we saw with Wile E. Coyote. What was its potential energy and kinetic energy? So potential equals the same value. So if the kinetic energy is equal to 0. So as a person falls, how do they change? Well, as the height decreases, so does your potential energy, because your potential energy depends on your mass and your distance and g. So if you decrease that distance, then you're going to see a decrease in your potential energy. And as your speed increases, so does your kinetic energy. All right, so that's what kinetic energy is, that energy in motion, and that potential energy is that potential to move, or that potential to cause damage. So this is also known as the conservation of mechanical energy. So this means that in closed systems with no outside forces acting on it, just like our conservation of momentum, there's no outside forces acting on it. It's a closed system to us. Mechanical energy is conserved. It does not change. And this is the law of the universe, okay? In math terms, your mechanical energy is equal to your kinetic energy plus your potential energy. And again, this is all within a closed system. So your mechanical energy initial is equal to your mechanical energy final, or your potential energy initial plus your kinetic energy initial is equal to your potential energy final plus your kinetic energy final. All right, with this time that I have left, let's talk about work. So work is a force acting upon an object to cause displacement. So work is equal to your force times distance. So we measure work in joules as well. So 1 joule is equal to 1 Newton force moving object at 1 meter. And forces at work at any part of force that does not act in the direction of motion does no work. We're going to talk about work and power. So power is your work over time, and power is measured in watts. So 1 watt is equal to 1 joule of work per second. 1 horsepower is equal to 746 watts. So increased power, more work in the same time, same work in less time.